Hello, and welcome back to the course on Physics for Engineers. We are still on the 8th chapter for this course. So before we proceed, let us first review some concepts. So in the previous lessons, we have discussed about resonance, the forced oscillation of an object when the driving force frequency matches the angular frequency of that object. We also have discussed about standing waves on a string, where we have shown that there are certain frequencies wherein the string will have resonance, or will resonate, or will create standing waves. And we call these frequencies as harmonics. So the frequencies are NV over 2L, and where N is 1, 2, 3, and so on. We also have discussed that in the standing waves on a string, there are displacement antinodes and nodes. Antinodes are maximum displacement points, and nodes are zero displacement points. So for this lesson, we are still on the topics about sound waves. We will discuss about standing sound waves and resonance. So similar with standing waves in a string, standing sound waves are produced by the interference of the incident and reflected sound waves in pipes. So if you have an open pipe, pipes that are open at both ends, or a stop pipe, pipes that is only one end is open, then you can have standing sound waves provided you have the right frequency. So this is an open pipe, and this is a stop pipe. So an example of an open pipe is a flute. A flute is an open pipe. The pipe in organs that you see in churches are usually stop pipe. So this is an example of the simulation of the vibration of particles in an open pipe. So you will notice that in an open pipe, the particles in this region here doesn't appear to be moving. So this is a node, a displacement node. But a displacement node is what we call a pressure antinode, a region of high pressure. So it's a compression, or it's a compression node. So high pressure. So please don't be confused. This is a displacement node here, the N, but this is also a pressure antinode, since we have discussed in the previous videos that sound waves are basically just pressure fluctuations. So in terms of pressure fluctuations, a displacement node is equivalent to a pressure antinode. And displacement antinode equals, or is equivalent to, or is where a pressure node, or a rarefaction region, or low pressure region is located. So that one. So for an open pipe, both ends are displacement antinodes or pressure nodes. And for a stop pipe, the open part is an displacement antinode or pressure node. Okay. So basically, this is what the vibration of molecules look like when there are standing waves inside a pipe. Okay, so similar with our discussion with the standing waves on a string, there are allowed frequencies in order to create standing sound waves or resonance. So for an open pipe, it's just exactly similar to the standing waves on a string, NV over 2L. But for a stop pipe, it's now NV over 4L. And instead of the integers to be all integers, it's now odd harmonics. Only odd harmonics are present. 1, 3, 5, 7, and so on. So the F1 for both open and stop pipes are still the fundamental frequencies. But the second harmonic, or the first overtone, for an open pipe, it's F2, the second harmonic or the first overtone. But for the stop pipe, the second harmonic is F3. The second harmonic or the first overtone is F3. That one. That's the difference. So the third harmonic or the second overtone For an open pipe, it's now F3, but for a stop pipe, the third harmonic or second overtone is now F5. So please take note of that. Only add harmonics for the stop pipe. Pipe open at only at one end. And these are the allowed wavelengths. 2L over N, exactly the same as the standing waves on a string, for a string fixed at both ends. And for a stop pipe, the wavelengths are 4L over N. So that one. So sound resonance is basically just forced vibration of molecules to produce sound. So in the case of the pipe that we have discussed earlier, you are actually forcing the air molecules inside the pipe to produce a certain frequency of sound. But in general, sound resonance can occur when you hit the natural frequency of an object. So the frequency wherein an object starts to vibrate. So in this example, you have a glass and it's in front of a speaker, and the glass starts vibrating until it breaks. So that's actually a manifestation of resonance. So it's similar to a feedback loop effect. So you may have encountered this phenomenon when you point a microphone towards a speaker and there's some amplification happening because it's a feedback loop. The speaker produces sound, the microphone picks up that sound, amplifies it, and then feeds it back again to the speaker. So there's a feedback loop effect. So what usually happens in this scenario, in the feedback loop effect, is that the sound will get intense and intense, and the frequency will get higher and higher. So that's also what happens in the breaking glass. The frequency of vibration starts getting higher and higher until the glass breaks. So that's basically resonance, sound resonance. So there's also resonance occurring in our ears, especially if there's a certain frequency that we hear. So our ear is actually like a stop pipe, open on one end, close on the other end. So it's a stop pipe. So we have only odd harmonics. There are only odd harmonics can cause resonance in our ears. So basically, we can actually calculate the fundamental frequency. It's actually around 3,440 hertz and multiples of this. So multiples of 3,440 hertz, actually odd multiples. So 1F1, 3F1, 5F1, 7F1, and so on. So our ears are actually very sensitive to this frequency. When we hear a sound with frequency of 3,440 hertz or near 3,440 hertz, it will create something like a feedback loop effect in our ears. And we don't usually, it's not a pleasant experience. So that one. So our ear is like a stop pipe. Okay. So similar also with our windpipe. It's also a stop pipe. That one. The way we create sound using our vocal cords. So there's a pipe that creates sound. So basically our the vocal cords are actually resonating with our pipe here to produce sound waves. Okay, let's have an example. So this is a comparison between an open and a stop pipe. So an organ pipe, a stop to organ pipe, maybe this is a church, has a fundamental frequency of 165 hertz. So the second overtone of this pipe has the same wavelength as a third harmonic of an open pipe. So how long are the two pipes? Assume that the speed of sound in the pipes is 340 meters per second. So the speed of, we are asked for the length of the stop pipe with fundamental frequency of 165 hertz and the second open pipe. So for the stop organ pipe, we know the fundamental frequency, 165 hertz. We know the speed, 340 meters per second. So basically, we can solve for its we can solve for its length. So F1 is just V over 4L. So this is a stop pipe. So we can solve for L, V over 4F. And we get the length of the stop pipe is 0.515 meters. Now, since we compare this with the second open pipe, and the condition is the second overtone of the stop pipe, that's F5, or in terms of wavelength, lambda 5, has the same wavelength as the third harmonic of an open pipe. Third harmonic of the open pipe is F3, or in terms of wavelength, lambda 3. So meaning, lambda 5 for the stop pipe is the wavelength of F5 for the second overtone of the stop pipe is equal to the wavelength of the third harmonic of the open pipe. So this is just this is stop pipe, so 4L over N, where N is equal to 5. And this is an open pipe, so 2L over N, where N is equal to 3. So you can now solve for the length of the open pipe, since we already know the length of the stop pipe. So it's this one. So you will get a value of 0.618 meters. So that one. So in this lesson, we'll just be focusing on the resonance or standing waves between open and stop pipes. And that is it for this lesson. So this is the second to the last lesson for this course. And the last lesson for not for this course, but for this chapter. So the last lesson for this chapter will be all about Doppler effect in sound. So I will see you again in the next lesson.